My name is Adam. The title is a bit of a mouthful, Deep Learning Solution Architect. Effectively, I'm a glorified mathematician. I know how to do one thing and one thing only. I build algorithms, and in particular, perception algorithms, so algorithms that see pedestrians as the car is approaching them, that see other cars as they move in front or on the sides of your vehicles, that see road signs, they perceive the world around us. And what I'm going to talk about today are challenges in building those algorithms. But before I do that, let's have a bit of a context, because I'm perfectly aware that not all of you know who NVIDIA is and why a company that you might associate with development of gaming products. So, computer cards that your children are using to play Tomb Raider. Why are we talking about self-driving cars at all? So we've discovered substantially more than a decade ago that exactly the same logic that is required to accelerate computer games can be used for scientific computing, because effectively computer games require a very efficient accelerator of linear algebra. So a very efficient accelerator of math. And we've capitalized on that discovery quite some time ago. And at this point of time, a very large proportion of the world's most powerful supercomputers are GPU accelerated. In fact, Summit, which is at this point of time the most powerful supercomputer, consists of 27,000 GPUs. So those are systems that are being extensively used to predict weather, to model seismic phenomena like earthquakes, to find oil, to discover new medicine through molecular physics, and to model astronomical phenomena like propagation of gravitational waves. On the back of that, we've noticed that a lot of artificial intelligence problems are becoming effectively high-performance computing problems. So quite several years ago, we've decided to invest a fair amount of engineering effort in building a fairly wide family of systems that shrink that high-performance computing, HPC capability, to the sizes and power levels that are appropriate not only for level 5 autonomy cars, but much simpler robotic systems, even including tiny little robots. But at the same time, we've discovered that it's not enough to build just the hardware platform, because actually the problem is surprisingly complex. So what we've started to do over the last couple of years, we've started to build what is now a fairly mature end-to-end system for autonomous driving. So we at this point of time, we have a fairly mature system for the vehicle itself, composed of sensors and a wide range of hardware and software components. We have a fairly mature solution to help train neural networks, which is the basic component that we use to detect pedestrians, to detect road signs. But also a fairly mature solution for software-based simulation, hardware-based simulation, and mapping. Within the car itself, we have an end-to-end, an open platform for development of self-driving functionality. It's end-to-end because it consists not only of the hardware layer, not only of basic components that are necessary to integrate different sensors together, but actually algorithms themselves. So algorithms that support the basic functionality that those systems require. On top of that, we also provide a set of algorithms to monitor the driver itself, because self-driving cars don't work in isolation. They work in tandem with the driver. There is a point where you have to hand over responsibility, and you have to do it in a responsible way. You need to hand over responsibility to the driver who's ready. This is already a fairly mature ecosystem of utilities, and we have a fair number of partners, developers on the NVIDIA Drive platform, so in excess of 370. Those include organizations such as Mercedes-Benz, Volvo, Audi, Volkswagen, OEMs, tier ones, so companies such as Zenuity, Bosch, ZF, Continental, but also mobility service providers, so companies such as Uber, and tracking companies, in fact. Moreover, what we've done, we've decided to shrink those solutions even further, and we have a very similar platform for robotics applications, which is already fairly well used across different industrial verticals. So that's something that we've been doing for a while. But coming back to perception algorithms, when we've started developing our initial round of software quite several years ago, we have very quickly noticed that that's actually a very complex problem. So there is an engineering gap, a substantial gap between building an initial system that exhibits first signs of correct behavior within a very narrow set of operational conditions, and a system that can robustly operate across billions, if not trillions of miles, because that's the reality of self-driving vehicles. Entire fleets will be operating for decades across almost an infinite linear combination of both environmental as well as geographical contexts. Those systems need to operate robustly, irrespectively of the weather conditions, irrespectively of where they are located. So not only the number of different algorithms that we need to develop is fairly substantial, because right now we're developing in approximately 20 different algorithms, so things such as perception algorithms to detect cars, pedestrians, pushchairs, bicycles, horse carriages, free space perception algorithms, so algorithms that detect how much space I have in front of me, distance perception algorithms based on cameras, weather detection algorithms, lidar protection algorithms, and many more. But we also need to prove that those algorithms actually work robustly. And that, given the context, given the sheer volume of those linear combinations, becomes a fairly complex task. So what we've noticed is that in order to succeed, we not only have to have a fairly substantial compute infrastructure to train and build those models, but even more importantly, we need to have a fairly substantial volumes of data to be able to reliably prove that those algorithms are robust. And what you're seeing here is a snapshot from our progress in October last year. This is kind of our data collection plan for this year. And those volumes of data are non-trivial. And just to give you a rough understanding of the implications of working with 180 petabytes of data, in order to even test those algorithms on such vast volumes of data in a reasonable amount of time, and you can decide what reasonable amount of time is yourself, but let's say in 24 hours, we will need 3,200 computers just to make a test. Yes, so that creates some fairly obvious challenges. Yes, and so to give you a slightly more compact understanding of where we are, at least in October last year, we had a rig which is widely available. It's called Hyperion. A lot of startups are picking it up from us if they want to use it, which has 12 cameras, radar, lidar, and we have a fleet of 30 cars that is driving globally, collecting the data. Even a small fleet like that is collecting in excess of 1 petabyte of data every week. And that's when we are selective about what we are collecting. That data set is now reduced to a data set of 15 petabytes. And you might think, OK, 15 petabytes is fairly manageable. A lot of large organizations will have Hadoop or other systems that deal with this amount of data. But in our case, the 15 petabyte data set is the hot data set. It's the data set that needs to be always available and is always worked on. So it's not the cold data that is being archived. That's actually the hot data set that needs to sit next to compute and be always available. And that causes some obvious problems. First of those problems is how do you even label that data set? It's a substantial problem. And as a consequence of that, we are now hiring more than 1,500 people working full-time, so 8 hours a day, labeling pavements, labeling road signs, labeling pedestrians. We have the capacity to label approximately 20 million objects a month across 20 unique models and 50 different labeling tasks. And then to be able to do something meaningful with that data, once it's labeled, we have in excess of 4,000 GPUs, so that altogether deliver 500 petaflops of compute. But that's just the beginning of the story, because that is just the capacity that we need to develop those algorithms. But then we need to, as I mentioned earlier, prove that they work. And part of that evidence is based in software, but there is nothing that can replace hardware. So we also have 100 Drive Pegasus systems that allow us to do very large-scale hardware in the loop tests. So this is what I meant. Testing on the road is extremely important, because that's the only way you can test certain aspects of vehicle operation. But it's just a small subset of all of the activities that mature team will have to execute. Those also include things such as software in the loop test, so atomically testing individual parts of your software solution, but also fairly large-scale hardware in the loop tests that we do with this system that you see here called Drive Constellation, which consists of two devices. One hosts an entire vehicle system in a data center chassis so that it can be placed in a rack. So you can think of it as a full automotive component placed in a data center. And the other one is creating a real-time photorealistic simulation that allows you to do regression tests and also make sure that you have extensive test coverage. So at those scales, systems matters, and we have realized that the hard way, because until you have the capability to develop the right data sets, so not just drive randomly, but be aware of where do you send your drivers and what data you're capturing, and then trim that data, until you know how to run the right experiments, instrument those experiments, and automate that process, ultimately, you will not be able to progress. Unless you solve those problems, adding more compute doesn't add any value, because you won't be able to use it. So this is an internal project that we've developed. Parts of it are available. Some parts of it are freely available, and I'll talk about it in a second as well. The project is called maglev, because that's, I guess, the fastest way to travel by train. And it addresses key elements of the engineering process. So data set lifecycle management, so capability to even deliver the data from that distributed fleet and land it in a data center, and then at such vast scales, make it available for labeling and for training. Machine learning pipeline automation, so a system that allows you to systematically execute your experiments, ensure that those experiments don't overlap, and ensure that your staff is actually learning from those experiments, because you need to fail 1,000,000 times before you succeed once. So, and finally, model analytics and insight. And again, at those scales, that's non-trivial. So we have a solution which is a hybrid solution. Part of it is hosted in the cloud, and part of it is hosted by us, where we have the capability to deliver data sets from our fleet of vehicles to the cloud data center, parse it, and then land it on fairly common set of technologies that some of you might recognize. So we land them in Parquet format, and we expose it to a wide community of users using technologies such as Presto, Spark, and Hive. And we do expose it to a wide community of users, because it's, again, not just about model development, but it's about data set engineering, about labeling, and quite a few other activities. And that system then allows us to do the training in a much more systematic way. And again, training is slightly more complex than just executing a training job on a set of deep learning models, because at some point, day-to-day driving is not contributing to your model development anymore. Your car already saw all of the day-to-day mundane driving activities. You're trying to address all of the corner cases. So a large part of that solution is an approach called active learning, where the artificial intelligence model itself is helping you to prioritize A, what to label, and B, where to send the fleet of your cars to collect new data. As I've mentioned, we have a fairly mature solution right now, distributed between a cloud and on-premise solution. So majority of our data lands in the cloud, is being heavily processed there, and it is being transported to our data center only after it undergone that fairly substantial reduction in size and is already aggregated and ready for further processing. Majority of our systems are orchestrated via Kubernetes platform, and I'll talk about software that is already available for you if you want to replicate some of it in a second as well. We have a fairly mature set of tools to help our research teams to understand the impact, the changes they are making on model performance at those fairly vast scales. So understand the impact changes to the models and data sets have on the algorithm performance. And we have a tool for automation and traceability. So we have a tool through which we can separate, isolate concerns, allow people to focus on their activity and have a clear understanding of the impact their individual changes are making, at the same time maintaining full automation of execution. So that's something that has been operational for quite some time, once again distributed between cloud and our own data center. We've learned a lot by building a solution for this problem, and we recognize that it's non-trivial. So that's a very high-level overview of how our data center architecture is designed. That's not really that important. What is important is the fact that we've invested a fair amount of effort in documenting it, and that documentation is available to you today. We've created a set of vendor-agnostic reference designs that you can use to both size, scope, and design clusters for all of the core activities, so both for training, software-in-the-loop simulation, as well as hardware-in-the-loop simulation and tests. So our Drive Constellation system is a major part of that solution. And that's more or less how, on very high level, from hardware perspective, it looks like. Bear in mind, this is also accompanied by a set of software utilities, again, which are open and in a public domain that you can use to automate, orchestrate, and manage your cluster, execute jobs. We really believe that we cannot build those solutions ourselves. So majority of the stuff that we do is open, and we're building it with a very wide ecosystem of partners. So it's fairly accessible. So we built, for example, our simulation ecosystem with companies listed here. And for years now, we are also working very closely with key bodies that are responsible for safety, because that's by far the most important concern. So we can capture all of the best practices at the very early stage of the process, of the development cycle. And that's everything that I had to say today.